Sure, so some of the test may have scared a few people away, but the good people are here. So, we're moving into something totally different, all right? So, let's take a big step backwards. Remember when we were first starting mechanics last semester, and we are actually starting class. All right, so what happened, last semester we had Newton's 3 force laws. And I told you at the time when I introduced them, I said there's really a way to think about these that's kind of simple. So, what's the basic idea behind the first force law? That's the second. If there's no acceleration, that's the conclusion. What was that?
It's the same amount of force acting on the other.
Alright, so when the net force is 0, there's no acceleration. That's one case.
Okay.
And once you have that case, everything else is the other case. Everything in the world, every idea can be broken into two pieces. The things that have this and the things that don't. Right? Well, the third law is a different story. So, but you understand, so what he basically said, look, there's forces and there's all of that. Alright, so in all the places on the earth where we have forces going on, if the net force is 0, there's no acceleration. That's the first law. Everything else is, if there is a net force, it's accelerating. And the acceleration equals the total force over m.
But we're ignoring the third one.
No, I'm not ignoring it. I'm just saying that the third law comes along trotting behind to say, by the way, this will help you think about first two. So the third one is not a calculation. If the third one's not a calculation law,
Okay.
the third one comes along and says, by the way, if you ever do have a force, there's going to be another one exactly equal to it going the other way on the other object. So it takes two objects to make a force, and those two objects exert equal and opposite on each other. All right? This introduces us to what we're going to be doing in a similar sense, and that there are two theories of relativity. One is called the special theory of relativity, and one is the general theory of relativity. And the way it works is very similar. If the net force is 0, we use the special theory. If the net force is not 0, we use the general theory. And I don't mean to insult you, but we will not be doing the general theory because no one in here is capable of understanding it, including the teacher. No, it's actually the general, but the general theory, in order to do it in any meaningful way, requires not just that you use vectors, but that you use tensors. And tensors are vector value matrices. And a lot of you don't even know what a matrix is, which is fine. In other words, that's why we're not going to do it. It's not required for the class. So I'll touch briefly on it, just enough for you to see where it comes from, but we're not doing any calculations. But we are going to spend some time with the special theory of relativity, and the good or the bad news, depending on how you want to look at it. The equations associated with the special theory of relativity really aren't too terrible. I mean, they're not lovely, but they're not too bad. But what gets hard is the brain-breaking way you have to kind of think about things. So to get started on that, I need to first get the idea, what do we mean by relativity to begin with? In science, if I talk about, what do you think of when you think of relativity? Or something being relative to something else? Does this chalk have kinetic energy?
What relative?
Good question. Because not relative to my hand, but relative to the sun, absolutely. We're going at like 29 miles a second around the sun. Do you understand the question now? So when I talk about relativity, it's essential in physics, because you might think you're sitting still, but you ain't. You're not even close to sitting still. Yeah, hurry.
So imagine two cars are moving in the same direction, the same velocity. So they're going to stationary with each other, right?
Okay.
And what if the both cars are accelerating in the same rate, the same direction? Will they be fixed with each other, like stationary with each other too?
Even if they're accelerating?
Yes.
Yes, but we'd be able to determine if they're accelerating even within the car itself, because the people in the car, if it's accelerating, would feel some odd force pushing them into the back of the seat. And they'd be able to measure it. So the deal that we're talking about with special relativity is not quite that. All right? What I was trying to establish with this is simply that relativity has to do with the reference frame you choose. So I'm saying that this has no kinetic energy relative to my hand, but it does have kinetic energy relative to the sun. And it actually does have acceleration relative to the sun because it's going around it. So I'm not really acceleration out. That all falls into general relativity, and we're not going to go there.
Okay.
So what we're going to concern ourselves with is situations in which there is no acceleration. But I'm sure you realize that I can approximate not accelerating on the Earth for very short distances because the curve going around the sun is not a very big one. It's going to look a lot like a straight line for very short distances. So that if I have an atom that decays and shoots out an electron in a millionth or even a billionth of a second, in that amount of time the curvature around the sun doesn't matter at all. Are you with me? So that's the kind of thing that we're going to get into. All right, so we talked about this in the lab. The little green thing we looked at, saw the circles that went in and out and all that kind of good stuff. But to kind of make sure that you understand where that came from, here's an example I want you to consider. I've got a river, and the river is flowing at 6 kilometers per hour down. Okay? And it's 1 kilometer across. So I have a boat that goes at 10 kilometers per hour across and back. But it goes, so that when I watch it, I see it go in exactly a straight line, across and back. Okay? Are you with me? All right, so then I'm also going to have another boat, and do not worry about the math on this. I'm just trying to get this idea across, all right? So just kind of work with it. It's going to go up 1 kilometer and back. So this is up 1 kilometer, and it's also, it's going to, relative to the water, it's going to be doing 10 kilometers per hour, but it's going to go up 1 and back, and it's going 1 and back. Are you with me? So do you agree that both boats have traveled 2 kilometers?
Yes.
Yes. Do they both take the same amount of time? No. Does everybody, yes.
I'm sorry, and you said that both travel.
So this one goes upstream a kilometer, back downstream to where it started, so for 2 kilometers.
Oh,
And then this one goes across and back for 2 kilometers.
okay, yeah.
So the thing is, what's happening is that what happens is this boat, you understand, it has to go upstream a little bit in order to get to end up going straight across. Right? Because, so what happens is what it really does is it aims like this, gets pushed downstream, and then aims like this and gets pushed downstream to get straight lines across and back. I'm not going to do all the math for this. I just want you to realize it's very simple to do this, punch it through. And we find out that these take completely different, I mean, they're very different. The two answers aren't even really close. They're very different amounts of time. This is what Michelson and Morley were doing with their experiment, where they had the beam go this direction and this direction. If there's ether and we're moving through it, just like the river, it's going to take different amounts of time for those to get the same distance back and forth. So that when we rotate that table, we should see fringes shift because they're trading their velocity one for the other. And that's why we should have seen the fringes. No fringes were seen. And no one could explain it. There was nothing that came along that said, yeah, that makes sense. Well, then Einstein was playing around with the physics, and it turns out, you know, that James Clerk Maxwell had actually derived this, but he died. The sad thing is, Maxwell had lived even like 3 or 4 more years, he would have done all of relativity before Einstein was even born. All right, but what happened? He died of stomach cancer just as he was at the beginning of it. And now that we know what the answer is, and we look at his last notes in his notebook, it takes another page of equations to finish and get the basis of relativity. But he didn't know where he was. I mean, he was on the brink, but not knowing where he was, he didn't realize he was standing right on top of E equals mc squared.
When did he die?
When did he die? It was in the late 1800s. So, I mean, it was not a big gap before Einstein came along, because Einstein did his work in the early 1900s. All right, so here's the thing that I want to have you see, though. When you talk about relativity and the thing that gets us going there, it was determined that the speed of light was 1 over the square root of mu naught epsilon naught. Now you may not remember this, and don't, because this first bit of this, you take notes if you like, but none of this is testable. All right, I'm trying to get you a picture so we have somewhere to see where this is coming from. If I were to put what we're kind of here, I'm in a room, the walls are closed, blah, blah, blah. Can we just by dint of thought, can I tell if I'm moving? Can I feel the Earth going around the sun? No. Why? I mean, it's moving like 29 miles a second.
Because you're moving with that too.
Because I'm moving with it, right? And there is a tiny, tiny, tiny acceleration, but it's so small I don't sense it. So in other words, I can't really tell that I'm moving. So if you were in a black box in the middle of space, just there, and you were to do an experiment, could you do any experiment inside your box to determine if you were moving at a constant velocity relative to something outside the box?
Say that again?
If you're in a black box, no windows, so all you are is just inside, you've got all the equipment you may want, but you can't look outside, can you tell if you're moving at a constant velocity relative to something else in space? No acceleration, no curving, just going in a straight line at a constant speed. Is there anything you can do inside this box without a window to tell if you're moving? No, because every physical force would cause an acceleration. So only things we can measure are forces. The only way we measure velocity is relative to something. Just like you said, that chalk has no kinetic energy. Well, relative to us, but it's got huge kinetic energy relative to the sun. Do you understand where I'm going? We don't sense it because there's no acceleration. The only thing we're really sensing would be accelerations. So what that tells me is that if somebody's sitting dead still, these are the values, these are the numbers they would measure, because these are constants. These are constants in the universe. This is how easily magnetism goes through space. This is how easily electricity goes through space. But if they're moving at a constant speed, even if it's a very fast speed, but it's constant, or a constant velocity, they also get the same numbers. Do you understand how profound that is? Nobody else did either. But Einstein took a look and said, you know what? The speed of light is equal to the 1/squared root of these two numbers, which anybody who's not accelerating gets exactly the same number. What does that tell you? The speed of light has to be the same for every non-accelerating observer, no matter how fast he's going.
Did you come to this conclusion by intuition or just by calculation?
Oh, who knows how Einstein's brain worked? No, he was largely intuitive, very, very largely intuitive. But he was not. He was very careful. So once he had an intuition, then he would proceed and find mathematical basis for it. But Einstein introduced the world of physics. I'm going to probably use this a lot, so you may as well get used to it. Einstein was German, and this is his word for thinking. So he had what he called Gedanken experiments. And we use the word in physics, we still say Gedanken, so even though we don't speak German, but you see, just do the experiment in your head, because we don't really have the equipment to do it. So he would do experiments, and here's what he imagined. Imagine that we have a flashlight that's turned on and shining through space. Now I begin to move in the direction that the flashlight is shining, and I start going faster and faster and faster. What would happen if I actually exceeded the speed of light? I could get ahead of the light beam and watch the flashlight turn off. Because I would see, when you first turn it on, the first beam comes out. If I went faster than light, I could get past that point. So what I'm seeing is I would actually see time go backwards. You get it? Like, if you're watching a movie, and the movie has, the life of the movie is going through space, then the entire movie is in space. Right? The very first light that started is here. If I go faster than light and I'm watching the movie, I can start watching the movie backwards because I can get ahead of where the light has already gone. So that's the same thing as saying time would have to run backwards. And that makes no sense at all, because if time could run backwards, cause and effect would get reversed. And you'd have effect, and then cause would follow. And nothing in science says that can happen. It's always cause and effect. Yeah, Melissa?
Wouldn't it just be the perception?
Yeah, see, that's the thing, is it's actually a measurement, because you can take photographs of it. It's not just how you feel, but you actually can take photographs of things happening the wrong way if you're going faster than light.
Okay.
Yeah, it is perception, but everything you see is perception. Everything you measure, in a sense, is perception.
So time is measured, so therefore.
Yeah.
I guess.
And so the main thing that we want to get is that this shows you that no matter how fast you're moving, you're going to calculate the same speed for light, and therefore the speed of light must be a constant. And it's not obvious right away how profound that is. But we know it's got to be a constant for another reason. How come light travels? We know we have a varying electromagnetic wave, so it's sinusoidally varying, it increases, it decreases, it increases, it decreases. And because of that, if I were to take a sheet of paper and look, there'd be a changing electric flux through the sheet of paper. And we learned that when you have a changing electric flux, it creates a magnetic field, right? That's right. So this changing electric field causes a magnetic field, and it causes a perpendicular. Now I've got a magnetic field that's also changing, but a changing magnetic field does what? It creates an electric field. And so light continually recreates itself. So you've got basically they're trading places. They're changing electric fields, creating the magnetic field, and they just recreate each other. If light begins to travel faster, what happens to the rate of change? In other words, if magnetism is doing this, but now I'm going faster, the change that occurs is happening over shorter time, so the change is bigger. So a bigger changing electric field would create a bigger magnetic field, which is now bigger and changing faster, creating a bigger electric field, and would grow into infinite energy almost instantly. Do you see it? If it changes too fast, then the change is what creates the other thing. So if the electric field is changing, it creates a magnetic. The faster it changes, the bigger change it makes in the magnetic field. So if it's moving faster, that means changes are bigger. If you have bigger changes, it doesn't recreate itself, it recreates something bigger than it is. And then that recreates something bigger than it is, and that recreates something bigger than it is. There's only one speed that light can exist and exactly recreate itself. Too slow and it dies. Too fast and it grows without limit. Just right, and it stays a beam of light at the same energy that it started with. I saw your question. All right. Okay. If this doesn't make sense, hi. You know, my name is John. We belong to the same club. This doesn't make sense. No, I can kind of get this point, but I'm with you if you say it doesn't. You know, it's like weird. It is weird.
You said light gets bigger than it is if it goes faster. What does
Like
it
what?
change to?
The energy of light would grow without limit.
Oh, energy. Okay.
All right. So what would happen is a small beam would become an infinite energy beam if it goes too fast, and a big beam would die away to nothing if it goes too slow. But if it travels at the speed of light, it exactly recreates itself. And that comes out of this equation. So what we learn is that the speed of light is a constant. That's the main thing I'm pulling out is the speed of light is a constant. So Einstein came along then, and by looking at this, he came up with what we call two postulates. And the first one is speed of light. It's worded in a lot of different ways. Is constant for all inertial, and I'll explain this in a second, reference frames. All right, so the speed of light is constant for all inertial reference frames. Inertial merely means not accelerating, right? So for all non-accelerating reference frames, the speed of light is a constant. All right? And I think I did. That's why I want you to. I think I actually gave you the second postulate first. So I think this is the second one. All right? And then in the first one, it's that the laws of physics are the same in all non-accelerating reference frames. All right? So that's actually so what we're saying is we don't have to, if we're in an inertial reference frame, if we're not accelerating, we don't have to change the laws of physics at all.
How do you come with that idea?
All right? Because you can't think of a way to find out if you're moving. You can only find out if you're moving relative to something, but if you're not accelerating, there is no experiment you can perform to determine that, which means they've got to be the same or we'd have found it out. Does that make sense? That's the way you reason through. So these are the two postulates that Einstein came up with, and they could show up on the test as a 5-point question at the end, but there's nothing more that we do with them other than just say this is where we get started. This is the start of all special relativity, is this idea. I kind of just have to sell it to you on the fact that if you're sitting in this room and you don't feel yourself moving around the sun, then you've already bought the first one. Right? If you can't tell that we're going around the sun, does the sun rise and set, or does the earth turn? How do you know that? Because it was told to you. In other words, you think, oh, those stupid people in the past who thought this other thing. And if you just know that because you've been told it, you're in exactly their same shoes. Why could two such differing ideas persist among human beings? They're very different. One is that the earth turns, and one is that the earth sits still and the sun goes around it. How could both those ideas exist if this postulate weren't true? Do you see what I'm saying? Is that nothing in your experience answers that question. Nothing. You have to be told that by somebody who's done some other experiment somewhere. So that's how we can know the first one's true. How can I know the second one's true? From the first one. Because the second one says everybody, and in the reference frame that's not accelerating, will find the same value for mu sub naught because it's just a constant, and they'll find the same value for epsilon sub naught because it's just a constant, and from that they would calculate the speed of light, and it will always be exactly the same number, because they're always going to get the same numbers for both of those.
Because of the laws of physics.
Because of the laws of physics, the same in all those other references. Plus, he said it breaks logic, in the sense that if you could go faster than the speed of light, you would turn clocks backwards. Literally, you would start getting younger.
Why?
Because it would reverse time. That's the thing. The consequence of going faster than the speed of light is it would reverse time. And that doesn't happen. Okay, 7 for some of us. No, actually, yeah, no. High on my list of things I don't want to do is live forever.
I still don't understand when you travel faster than the speed of light, you go backward.
It's the main idea of that is you can kind of think of it. This is only one idea, but there's other proofs of it way beyond the scope. It's that idea of watching a movie, right? If you have a movie, let's say it's playing at a drive-in, all right? So outside, so the movie hits the screen and the screen reflects at the air, from which it travels forever, by the way, right? So if we had the ability to capture that light and traveled into space, every moment of that movie is somewhere in space, hopefully in chronological order. Right?
Beginning of the movie is a black spot.
The beginning of the movie's here, and the end of the movie's here, and it's traveling this way.
Yes.
The whole movie's there. If I travel this way, I see the movie. If I travel this way, I see the movie backwards.
Okay,
Right? You're giving a strange look. Do you understand? If the movie plays, all the time it's playing, the light from the first screen is already well into space before the light from the last screen gets launched.
Okay.
Right? Light's been traveling into space from the very beginning. So the entire movie is somewhere in space, and if I travel with it, I can see a frame frozen. If I travel faster, I see the movie run backwards. If I sit still, I see the movie in order because it moves past me. Right? So when you watch a movie, you're staying still, but the movie is going past you. Strictly speaking, if you're in the first row of the theater, the people in the back row see the movie after you do.
Wait, what?
All right. I'm here doing an experiment. Oscar sees the experiment before you do.
Okay.
Because the light gets to him first before it gets to you.
That's true.
It's true. That's right. Nothing you see is now. Nothing you see is now. Everything is later.
Like our nouns are all different. Right?
Everybody has different now. All right. Now, I mean, this is highly philosophical, guys. So, I mean, we'll play with it for a bit, but then I'm going to move on to something less philosophical. Yeah.
I have two questions. So
Sure.
one, is time measured by light?
Oh, yeah.
No, and yes. So it turns out that time is actually measured by the vibrations of electrons around a particular cesium atom. But ultimately, to make the speed of light a constant, we change the length of a meter to make the speed of light exactly a number. Right? So because light's the only constant in the universe, as we're going to find out, then the length of a meter was defined in terms of how far light travels in a certain amount of time. But we're going to find out time is not a good basis for measuring things, because time does change.
And then one more thing, when you said the speed of light is for something that's not moving, but it's, what would change?
No, I didn't say not moving, I said not accelerating.
Accelerate, okay, so what if you're accelerating in a car? Does
You
that
actually change the speed of light slightly. Now, it would take, here's the thing, we're going to find out, you have to be going probably about 30 to 40% of the speed of light to make even a halfway decent measurement of the change.
Okay.
But we now have many situations in which we can do those experiments Whereas when it first came up, there was no way to do it. Now we can make the actual measurements and find out that yes, it changes. You got a lot of questions. Is that question, Stan? Or just
Yeah, so if you start accelerating, let's say 30% of the speed of light, then you notice a change in the speed of light, right? Or
correct. But the other thing that's going to be odd is if you have a certain acceleration, it will take you an infinite amount of time to reach the speed of light. So if you're accelerating at a third of the speed of light, it turns out that it takes you an infinite amount of time to get to the speed of light because the faster you go, the greater your inertia becomes and the harder it is to move you. Your mass approaches infinity while your speed approaches the speed of light. This is all down the road. We're not ready to go here yet with all of this, so yeah, weird stuff. Okay.
Going back to the movie experiment. So the wave for the movie is in space now.
Yes.
And now, is it possible for me to go behind?
By the way, I'm using this example. You understand that this has no reality in
Sure,
reading
sure.
it. Okay.
If I imagine I'm behind the wave, now the wave is moving that way.
Mhm.
I'm behind the wave, but there is no way I can see anything from that. It's only
No.
in one direction.
We're going away from it.
So, and when I do the velocity speed of light, is the vector quantity too always?
The speed is not a vector,
Vector,
no.
yes.
But if you want to talk about the direction of the light's traveling, I mean, we could assign that a velocity
Okay.
vector, yes.
Okay, we can. Okay.
Oh, was that the question?
That I'm just getting my head around the whole process.
Okay. So, Tomas, was that a
Oh, wait, so like, time travel would only be possible if you go faster than the speed of light?
time travel? Do you want some really bad news? Time travel in itself is not possible unless you can warp from one time to another. The actual traveling through time, at least whenever I say not possible, you understand, we all,
From what-
given our current understanding,
Yeah.
right? And if time travel were possible, where are the time travelers? Do you understand the question? I mean, so if you can travel in time, then people from the future should come and show us how to do things right.
You're right.
Maybe we don't really.
They should be here.
Or they want to.
Or they're here already and they're the ones who are doing all the nasty stuff. All right.
What if it's a butterfly?
All right, so guys, let's stay focused because there's a lot more I've got to go through here. So I need to stay focused. All right, so the other thing is we have another notion that I'm about to throw away, and that's simultaneity. So here's the thing. Once he comes up with this idea that the speed of light is the same for all observers who are not accelerating, then some very odd things happen. And because he always uses train cars, we're going to play right along with it. All right, so here's the deal. I've got Maria sitting here. Please don't be offended, either of you. And I've got your dead center in the car. All right? And I've got a little light here, and I've got a little light here, equal distance from you. Okay? And somebody is standing here outside, and this is moving in this direction at a very high velocity. Okay? So you got the picture, we've got a train car moving at a high velocity, but not accelerating. Not accelerating. Everybody with me on that? When the car gets to where I'm exactly lined up with Maria in the middle, I hit a switch and both those lights flash at the same time for me. I see them both flash at the same time. Do they flash at the same time for Maria?
Yes.
No. And that's what's weird. But let's think about it. So the light here starts, and the light here starts, but she's moving that way. So she catches up to this beam before this beam gets to her. So I see them happen at the same time because I'm not moving. So when they flashed, the light came from the same place all the way to me. I saw them simultaneous. But she moved forward and saw this beam before she saw that beam. So she swears, no, this one happened first and then this one. So what we learn is that things being simultaneous is completely dependent on your reference frame. It's not a basic nature of physics to say something is simultaneous. If something is simultaneous in one reference frame, it absolutely is not simultaneous in a different reference frame. It's moving.
Now, the passenger is in the car. right?
Yes.
And when the light,
Well, I hit the switch when the car is halfway, so that these two lights are equidistant from me, so when I hit them and those lights flash, they travel the same speed, I'm not moving. Once the light has left those lights, I mean, it's
If
just,
if I'm not moving, the train is moving related to
the
me.
train is moving this way past me.
Past me, okay?
All right, and when she's lined up with me, those lights flash, which means they have the same distance to travel to get to me, and I'm not moving relative to them, so they will arrive to me at the same time. I call that simultaneous.
No, it's,
Simultaneous means I see the lights flash at the same time.
it's on the car, the light is on the car, right?
Right.
So if light is on the car and the passenger is looking at the car, isn't the passenger is stationary relative to the car?
The passenger stationary with respect to the car, but that light goes in every direction.
Okay.
Right? And so as she moves forward, she's going to intercept this light before this light catches up to her.
Okay.
So our wavelengths for light, they're not disturbed by anything, so if you hit the switch and it's moving, we're still going to be...
Actually, yes, they are, and that's one of the reasons why, if you've ever heard people talk about the redshift in the galaxy, that we find that all the galaxies are redshifted. That's because their wavelengths are perturbed because they're moving away from us. So there is a change in the wavelength due to the motion. Actually, a very good question. All right, all I'm trying to tell you right here is that simultaneity is gone. So simultaneous only works for a given reference frame and for no other reference frame. This is just to make sure that you understand that, wow, this is really weird. All right, and now I'm about to do something highly mathematical. This will not be on the test, but it's really, really important that you follow it, because if you don't, then you'll just be memorizing an equation. You won't know why I'm doing it. All right. So I need you to follow through on this and to sort of understand what's going on. Because of this problem we've got, we introduce the word proper. And in relativity, when you do proper, it's a measurement in a system you know what? It turns out I was trying to make something easy. I have to give two definitions. All right. So what I'm going to do is I'm going to put them over here, and we'll do two separate definitions: proper length and proper time, because there's not one definition for works for both. Proper length is the length of an object at rest with respect to, are you okay with that abbreviation? WRT with respect to? All right, with respect to the observer. All right, so somebody stole my meter stick. Why did they steal my meter stick? Anybody see the meter stick floating around anywhere? I'm not sure what this is. It's like somebody set up an experiment on my freaking sheet. So I'll see it. All right, so if you were to measure the length of this rod, are you going to measure a proper length? So because you're at rest, is at rest, this is going to be a proper length. If I walk in front of the room like this and you measure the length, strictly speaking, would you measure a proper length? No. Although at those speeds it won't be very different. All right? Now, proper time's the one that's tricky. It's the time between